Hi students, today I will explain about formal charge. Okay, so yesterday I completed Paget's rules. Okay, no. So next topic I will continue today. So that is a formal charge. So what is a formal charge? So formal charge is possessed charge of atom. Okay, so when a molecule has two more structures, so those two more structures are called as resonance structures. Okay, so when a molecule has resonance structures, then only this formal charge will be given. Okay, so for that example, ozone. Now, how we find out formal charge for any atom? So for that, here a formula is given, that is a number of valence electrons minus number of bonds around that atom minus number of paired electrons. Okay, so formal charge of any atom is equal number of valence electron of that atom which we are finding, and the number of bonds around that atom, and minus again number of paired electrons. Okay, so it will be explained with example. Now here I took that ozone molecule. These two are the resonance structures of ozone molecules. Okay, so here in these resonance structures, in first compound, the double bond is present in this direction, whereas in other structure, the double bond is present in other opposite direction. Okay. So now I wrote that first oxygen atom, second oxygen atom, third oxygen atom. Okay. So now first I have to take off formal charge on first oxygen atom. Formal charge on first oxygen atom. Okay. So that is called the number of valence electron. Oxygen belongs to 68 group now. So therefore its valence electrons are 6 minus number of bonds around this atom. Around that first oxygen atom, number of bonds are 2. Okay. So minus number of paired electrons. So two pairs are there, but those paired electrons are 4. So that's why here I wrote that 4. Therefore, formal charge on first oxygen atom is first oxygen atom is 0. Okay. Next, formal charge on second oxygen atom. Here again valence electrons are 6 minus number of bonds around that oxygen are 3 minus number of paired electrons are 2. So therefore it possesses plus 1 charge. So, so that's why here I wrote that plus only. Okay. And next, formal charge on third oxygen atom. So here number of valence electrons are 6 minus number of bonds. Beside of that oxygen atom is 1 only, minus number of paired electrons. 3 pairs are there. So therefore number of paired electrons are 6. Therefore that is equal to minus 1. So here I indicated those charges. On first oxygen atom, neutral charge is given. Okay, there is no charge, means that indicates neutral. And second oxygen atom has plus 1 charge. Third oxygen atom has minus 1 charge. Okay, in the same way here also. And next, other example, that is of nitrous oxide. Nitrous oxide N2O. Okay, so first write resonance structures of nitrous oxide. So this is first structure and this is second structure. In first structure, in between of nitrogens as well as in between of nitrogen and oxygen, double bonds are present. Okay, here double bond is there and here also double bond is there. But in other structure, in between of two nitrogen atoms, triple bond is there, and in between of nitrogen and oxygen, a single bond is there. Now, here all the atoms are different. Okay, so that's why here I given the number for each atom. So now find out formal charge on first nitrogen. So its valence electrons are 5 and number of bonds on beside of this nitrogen are 2 minus number of paired electrons are 4. So that is 5 minus 6. So that is equal to minus 1. Therefore, here I kept that minus charge. And next, on second nitrogen atom. On second nitrogen atom, number of valence electrons are 5 minus 4. Number of bonds are 4 minus 0. Because here there are no paired electrons. So therefore I wrote the 0. And then that is equal to plus 1. Therefore here I kept plus 1 plus charge for this nitrogen atom. And next, third atom of oxygen. Okay. So on third atom of oxygen, number of valence electrons are 6 minus number of bonds are 2 minus number of paired electrons are 4. So therefore it possesses neutral charge. Okay. And next, fourth nitrogen atom. Formal charge on fourth nitrogen atom. See here, 5 minus number of bonds are 3 minus number of paired electrons are 2. That is equal to 0. It has no charge. Okay. On fifth nitrogen atom, 5 minus 4 minus 0. So it possesses plus 1 charge. On sixth oxygen atom, 6 minus 1 minus 6. Okay. So that is equal to minus 1. Therefore, here I kept the minus charge. Okay. So this is about formal charge. This is about formal charge. And next, one of the important topics that is of dipole moment. Okay. So dipole moment is the product of charge and the distance between two atoms. Okay. So this dipole moment is the product of charge on the pole. Pole means on any one of the atom into the distance between. It is the product of charge and distance. Charge and distance. So charge Q indicates the charge on the pole. D indicates the distance between two poles. Okay. So example wise, here I took hydrogen fluoride molecule. In hydrogen fluoride molecule, hydrogen belongs to first group. Therefore, it possesses partial positive charge. And fluorine belongs to seventh A group. Therefore, it possesses partial negative charge. Two opposite poles of substance is called as polar substance. Polar substance. Okay. So therefore, the dipole moment is explained for this type of polar molecules. Okay. And now, what is the unit of dipole moment? So its unit is dBi. The unit of dipole moment is dBi. So 1 dBi is equal to 3.33 into 10 to the power minus 30 coulomb into meter. Coulomb into meter. So that coulomb into meter is the SI unit. dBi is not the SI unit. Okay. Coulomb into meter only the SI unit. And that 1 dBi is again equal to 10 to the power minus 18 ESU centimeter. Okay. So here that was given in coulomb into meter and here it is given in ESU centimeter. So this SI unit is coulomb into meter, CGS unit is ESU centimeter. Okay. So therefore remind this 1 dBi value is equal to these two. And this mu is one of the vector quantity. Okay. So vector quantity. Therefore it is always represented with cross-headed arrow mark. It is always represented with cross-headed arrow mark. So how that indicates that cross-headed mark is indicated from low electronegative atom to high electronegative atom. See in this example, I took that hydrogen fluoride. Hydrogen is low electronegative atom. Okay, so therefore a tail pot is here. And next head pot is indicated on the high electronegative atom. Okay, so here this is tail pot and this is the head pot. Head pot is denoted on high electronegative atom and tail pot is indicated on less electronegative atom. And next, calculation of resultant dipole moment. In which conditions the dipole moment is calculated? Okay, if two polar bonds are inclined at angle theta. So here I took one of the molecule that is of ABC. Okay. So this AB is one kind of polar bond and AC also one kind of polar bond. These two polar bonds are inclined at angle theta. Okay. So then the resultant dipole moment is calculated. So that resultant dipole moment is calculated that mu is equal to under root mu1 square plus mu2 square plus 2 mu1 mu2 cos theta. Okay. So the resultant dipole moment when two polar bonds are inclined with an angle, then the resultant dipole moment is calculated with this formula. Okay. So see that for AB bond, dipole moment is given that as mu1. For AC bond, dipole moment is given as mu2 and theta value also given. So that's why with this we will find out. And next, applications of dipole moment. This is also important topic. Okay. So what are the specialties of dipole moment? So it is helpful in predicting the geometry of the molecule. Okay. So means what? How it predicts for linear, trigonal planar and tetrahedral molecules. Dipole moment is always zero. Okay. So for linear molecule, trigonal planar molecules and tetrahedral molecule, dipole moment is zero. Okay. So see the example here in carbon dioxide molecule. It has linear structure. Okay. So now I'll explain with some explanation. So listen, carbon is less electronegative atom compared to oxygen. Okay. So center atom is carbon and sidewise atoms are oxygens. No. So here dipole moment is indicated from carbon to oxygen. Okay. So that's why that sign will be from carbon to oxygen and here also from carbon to oxygen. Okay. So here two polar bonds are present. Okay. So but those two polar bonds are two opposite directions. Okay, so those are two opposite directions. Therefore, the dipole moment of one bond is cancelled by the dipole moment of other. Okay, so therefore, its final dipole moment is zero. So its dipole moment is zero. Okay, and next for trigonal planar molecules. So boron trifluoride has trigonal planar structure. Trigonal planar structure. Okay. So in this case, the dipole moment of this bond is calc- cancelled by the dipole moment of these two bonds. Okay. So dipole moment of this is cancelled by the dipole moment of these two bonds. So therefore, here also dipole moment is equal to zero. So this is one of the application. And next, this dipole moment can separate symmetrical and non-symmetrical molecules. Okay, how it separate? For symmetrical molecules, dipole moment is always equal to zero. Okay, so that is example carbon dioxide, beryllium chloride, and trans compounds. All these are the symmetrical molecules. I will explain with examples. And next, see here in this example, I mentioned that cis molecule and trans molecule. Okay, so cis molecule. These are 1, comma 2 dichloroethene. Okay, here I took the example as 1, comma 2 dichloroethene. Okay, so this is cis molecule and this one is trans molecule. Okay, so now I indicated the cross-headed arrow marks. Okay, for each polar bond. Just you observe that. Okay, the dipole moment of this bond is cancelled with this, and the dipole moment of this are cancelled. So in trans molecule, so trans molecules are symmetrical molecule. Trans molecules are symmetrical. Due to symmetrical structure, its dipole moment is equal to zero. Okay, but cis molecules are non-symmetrical. Therefore, for cis molecule, dipole moment is not equal to zero. Here we need not to take up the value. Here just you have to concentrate for which molecule dipole moment is 0 and for which molecule dipole moment is not equal to 0. So always remind this, for trans molecules dipole moment is always equal to 0. That is due to its symmetrical structure. Okay. And next, here one more example I took. When we compared the dipole moment of ammonia and dipole moment of nitrogen trifluoride. Okay. So dipole moment of ammonia is more than dipole moment of nitrogen trichloride than nitrogen trifluoride. Okay. So in all this, I wrote the clear structures. Okay. I wrote the clear structures. First, I will explain about ammonia. Okay. In ammonia, hydrogen atom is less electronegative atom. Therefore, here three upward directions are given. Three upward directions are given. Okay. So dipole moment are always indicated from less electronegative atom to more electronegative atom. Okay. And next, see about nitrogen and lone pair. So that lone pair of electron of orbital also more electronegative. Therefore, here also that indicated in upward direction. Okay. So therefore, here all four the directions are in upward side only, in one side only. So therefore, the dipole moment of each bond is added. So therefore, dipole moment of ammonia is greater than dipole moment of NF3. In NF3, in nitrogen fluoride trifluoride molecule, nitrogen is less electronegative than fluorine. Therefore, here directions are indicated from nitrogen to fluorine. Okay, so one direction only in upward side and remaining three are downward directions. Okay, so therefore its dipole moment is here these two are cancelled with each other. Just two directions are only there. So therefore its dipole moment is less than this ammonia. Okay, and here dipole moment of cis molecules are always greater than dipole moment of trans molecule. Okay, and next some more examples are there in ortho meta and para compounds. Okay, so already we know about ortho molecule, meta molecule, para molecule. So first we have to see about para molecule. For para molecule, dipole moment is always equal to 0. So why it is 0? Due to symmetrical structure. Okay, so due to symmetrical structure. And next, for ortho molecules, dipole moment is more than meta molecules than para molecules. Ortho, for ortho substances, dipole moment is greater than meta than para. Okay. And next, here, again different molecules are given. So now in these molecules, just I mentioned that mu is equal to 0, not equal to 0, not equal to 0. Okay. So why? For this molecule, mu is equal to 0. So why? Because it has symmetrical structure. It has symmetrical structure. And in these compounds also symmetrical structure is there. But that oxygen atom has paired electrons as well as sulfur atom also has paired electrons. Just now I said that. For paired electrons, electronegativity is more. So therefore, symmetrical structure is not explained to these two molecules. Therefore, dipole moment is not equal to 0. Okay. So for this only dipole moment. Here paired electrons are not present. So therefore, it has symmetrical structure due to that its dipole moment is equal to 0. So simply we'll say due to its planar structure dipole moment is 0 and due to non-planar structure its dipole moment is not equal to 0. And some more examples also given. So chloromethane dipole moment is always greater than dichloromethane, than trichloromethane, than carbon tetrachloride. Okay, chloromethane dipole moment is greater. Okay, than dichloromethane, than trichloro, than tetrachloromethane. So see the structures, then you will get that. Okay. So next, dipole moment is always directly related to electronegativity difference. Electronegativity difference means on increasing electronegativity difference, dipole moment is increases. Okay. So on increasing electronegativity difference, dipole moment is increases. So in HF, dipole moment difference is more. Sorry, electronegativity difference is more. So therefore, for hydrogen fluoride molecule, dipole moment is greater than hydrogen chloride than hydrogen bromide than hydrogen iodide. Okay. And this dipole moment is directly related to number of lone pairs. Means what? On increasing number of lone pairs on the center atom, dipole moment increases. Dipole moment increases when the sidewise atoms are similar. When the sidewise atoms are similar. Now see these examples. Hydrogen fluoride, water, ammonia. So in hydrogen fluoride, on fluorine atom, three lone pairs are there. In water molecule, on oxygen atom, two lone pairs are there. In ammonia, on nitrogen atom, one pair is there. Okay. So due to having more lone pairs, its dipole moment will be more than water than ammonia. So therefore, on increasing number of lone pairs on the center atom, dipole moment also increases. Okay. So when the sidewise atoms are similar, when the sidewise atoms are similar. And next point, the percentage of ionic character of a covalent bond is calculated with this dipole moment. Okay. So with this dipole moment, the percentage of ionic character is calculated. So, so that is by using this formula. So that is equal to observed dipole moment by calculated dipole moment into 100. Okay. So the related problems will given in next classes. Okay. So maze wise as well as need wise related questions are there or previous questions or other questions. I will be explaining further classes. Okay. So that's why compulsory you watch this class. The percentage of ionic character of a covalent bond is calculated. So that is calculated by using this formula. Observed dipole moment by calculated dipole moment into 100. Okay. And now, next point. If the electronegativity difference between two atoms is equal to 1.9, if the electronegativity difference between two atoms, okay, so two atoms that is equal to 1.9, then the compound will be, the molecule will be 50% ionic and 50% covalent. Okay. So 50% ionic, 50% covalent. And if the electronegativity difference between two atoms will be greater than 1.9, then the compound will be more ionic in nature. More ionic in nature. And next, if the electronegativity difference between two atoms is less than 1.9, then the compound is covalent in nature. The compound is covalent in nature. Okay. If electronegativity difference is given, that is of Xa minus Xb in the problem. Okay. If electronegativity difference, that is Xa minus Xb is given, then the percentage of ionic character is majorly calculated with this formula. Okay. So that is of 16 into Xa minus Xb plus 3.5 into Xa minus Xb whole square. Percentage of ionic character. In which condition, if they given the Xa minus Xb value only, then the percentage of ionic character of the compound is calculated by using this formula. That is of 16 into Xa minus Xb plus 3.5 into Xa minus Xb whole square. Okay. So objective purpose, some problems are related to this. So that's why compulsory you remind this formula. Okay. And next topic, that is of resonance. Next topic, resonance. So what is resonance? So resonance is representation of molecule in more than one structure, and none of them explain all the properties of the molecule singly is called resonance. Okay. So generally we know about benzene. Okay. So in benzene has two resonance structure. No? One is this structure and the other one is this structure. So that resonance structures are formed by the displacement of electrons, by the displacement of electron. Okay, displacement of pi bonds. But here resonance means representation of molecule in more than one structure. So generally for all the compounds, one structure only give. For some compounds, more than one structures also give. Okay, so in that case, this resonance only explain, but none of them explain all the properties of the molecule. Okay, all the properties of molecules are not explained with single structure. So that's why these resonance structures are given. So that is only called as resonance. And next, bond order is calculated with resonance structures. Here important point. So bond order is calculated with resonance structures. How we calculated? Bond order is equal number of bonds in between two atoms in all structures by total number of resonance structures. Okay, I will explain with example. Now let me take nitrate ion. Nitrate ion. Its bond order is 1.33. How we got that? So see its resonance structures. Okay. So in resonance structures, see you observe that in this compound, double bond is here, and here double bond is here, and double bond is here. So here all the bonds are changed their places. Okay. So that's why these three compounds are called as its resonance structures. Okay. So now how we calculate the bond order? Bond order of nitrate ion is equal to 4 by 3. So 4 is what? Number of bonds in between two atoms. See, just you have to take off center atom. Okay. And around that center atom, how many bonds are there? One, 2, 3, 4. So 4 bonds. Okay. By total number of resonance structures. Total number of resonance structures. How many structures are possible for nitrate ion? Three structures are possible now. So that's why the total number of resonance structures are 3. Therefore, its bond order is 1.33. Okay. So here I wrote that number of bonds in between two atoms in all structures. Suppose if we take nitrogen and oxygen only. Okay. So here two bonds are there. Here third bond is there. Here fourth bond is there. So that is also similar. Or simply write number of bonds around the center atom. Number of bonds around the center atom. Okay. So by total number of structures. How many structures are there? 3. Therefore its bond order is equal to 1.33. And one more example is that perchlorate ion. Perchlorate ion. Its formula is ClO4 minus. Now I wrote its resonance structures. Okay. In these resonance structures, how many resonance structures are possible for this? 4 are possible. Okay. And now the bond order of chlorate ion is equal to 7 by 4. Okay. So see that around chlorine atom, how many bonds are there? 2, 4, 6, 7. So totally 7 bonds are there. By how many structures are possible? 4. Therefore, its bond order is equal to 1.75. Its bond order is equal to 1.75. So this is about bond order. Okay. So that bond order is calculated with resonance structures. So that's why I explained resonance structure. Resonance. Okay. So this is enough.